Okay, so we got our cart here. Let's say it's 2 kilograms, and we run the lab data. Our goal is to find what's the average force on this cart when it crashes into our wall over here. So we collected data. We collected velocity time data, and it looked like this, where it was coming in at a relatively constant velocity, and the crash happens right here at 1.2 seconds. It was going 3 meters per second. The velocity dropped off to 0, and then it started going back the other direction. It bounced off and got away from the actual wall. So then when it actually left, the crash ended. So the crash starts here, it ends down here when it's going -2 meters per second, negative because it's the other direction. That happens at 1.4 seconds. Okay, so what do I do with all of this if I want force? That's what we're trying to figure out, the actual average force that's being applied on that cart at that moment during the crash. Well, we know that the impulse is force times time, and that impulse causes a change in momentum. So, with mass and velocity, we can find momentums, and really the mass doesn't change, it's really just the velocity that changes. So, this is mass times delta v. Okay, so let's plug in the stuff that we know. The time, well, which time do I use? I want actually the time that the crash takes, so the duration of the crash. So really 1.4 seconds minus 1.2 seconds. All right, I know the difference between those. My mass was 2 kilograms. My delta v is final minus initial, so the final velocity was -2 meters per second. The initial velocity minus the initial velocity, so minus 3 meters per second. And now let's crunch some numbers. Okay, force times the whole crash lasted zero point 0.2 seconds, 2 kilograms, and my delta V is -2 minus 3, so it actually changed -5 meters per second. I'm going to divide both sides. Well, I'll do one step at a time. Let's say keep this for now. 0.2 seconds. 2 times -5 gives me -10 kilogram meters per second. So what's my change in momentum? That's -10 kilogram meters per second. Move my face out of the way. So now I divide both sides by the time, divided by time, and I get the force, on average anyway, is equal to 10 divided by 0.2. Let's see, divided by 2 would be 5, divided by 0.1 would be 50. So I'm going to say this is 50 without grabbing a calculator. If I make a mistake, learn from it. And that's kilogram meters per second, otherwise known as, defined to be, 1 Newton. So on average, during that crash, the cart experienced -50 newtons. How can we have a negative force? Well, it's going to the left. And I already, over here, kind of decided that the cart was going to the right. So, and I called that a positive number here. So my negatives are to the left, positive is to the right. So that gives me the average force during a crash.